All right, this video is going to go from a potential energy that we introduced last video to just potential, electric potential. So what we're doing here is very analogous to what we did before. So before we had Q equals F, or sorry, F equals Q times E. The electric force on a charged particle is that probing charge times the electric field that it's in. So the electric field is existing everywhere in space, and then a charge could experience an electric field and experience an electric force that's given by this, the charge times the electric field. So what we're going to do here is now take this potential energy that we defined, that we talked about last video, and we're going to say a charge is in something, and then when it experiences that, it's going to have a potential energy. So like potential energy per unit charge. And this thing right here is going to be electric potential. Okay, so that's the idea here. There's a bunch of source charges that set up a electric potential. And then if you had a probing charge or a test charge that you put in the electric potential, it will have some associated potential energy with that. So this is electric potential, not electric potential energy. Potential energy is U, the electric potential is V. So notice right away it's a scalar. Like what's nice about this, both U and V, is that we don't have to worry about these vector signs. So no components. We do have to worry about plus and minus signs, but we don't have to worry about components, which is great. So your book is explaining this, that the source charges create a field. It's a scalar field, not a vector field. So there's a bunch of so at every point in space, there's some electric potential. And then if you put a charge there, there's some associated potential energy with that. Okay, so so this formula right here is this right here. And a lot of times, actually, the way we use it is that a charge will move from one point to another. And so the change in potential, remember what's relevant is changes in potential energy a lot. The actual potential itself doesn't really mean all that much. But the change in potential energy is Q, whatever charge is moving, times the change in electric potential that it experiences. And this is the thing that's physical. So like when you plug something into your wall outlet, the potential difference, so actually it's complicated because it's AC, but the electric potential difference, say, is 120 volts. So that would be from one point to another, there's a difference, there's a potential difference. Delta V is 120 volts. And then if a charge goes from one end to the other, there's some change in potential energy. Or this is probably a better example because it's just DC. This side is at, so if this is point A, and sorry, there we go. So if this was point A and this is point B, these two ends of the battery, then VA minus VB, or delta V here, is going to be plus 1.5 volts. So one issue here is that, so 1.5 volts, delta V is 1.5 V. So one issue that we're seeing already is that the unit for potential difference is the volt. And the issue here is that the symbol used for volt, capital V, is the same thing as the variable. So this is a variable, and then this is a unit. So this is kind of unfortunate because you might have an equation that's something like this, V equals 5V. You can't just cancel out the V's and say, well, 1 equals 5. That's not what's meant here. What's meant is that the electric potential at some point in space would be 5 volts. So just be aware of this confusion that, you know, the V can refer to a variable or a unit. So you got to be a little careful. You might want to write out the word volts every time. And the unit here is such that, you know, this has to be true. So it's the SI unit of energy divided by the SI unit of charge, right? If I divide both sides by Q. So it'd be, so 1 volt is defined to be a 1 joule per coulomb. You know, we already know what a joule is, we already know what a coulomb is. So a volt is a joule per coulomb. All right, using the electric potential. So the electric potential is a property of the source charges, right? So it just exists in space. So a lot of times, so, you know, in this section, what's drawn right here is that we just have something that exists because of everything else in the universe. So we're kind of ignoring all the source charges and just looking at a single test charge that's moving in this thing. So in this figure, there's a direction of increasing V. Later, we're going to have, we'll see this already by the end of this video, we're going to have equipotentials. So the direction of increasing B means that the potential right here is greater than the potential at other points. So maybe this is 9 volts, 8 volts, 7 volts, etc. So the direction of increasing B would be to the right, the direction of decreasing B would be to the left. So what happens if you put a positive charge in the middle of this region, right? Remember that if you pretend you released a positive charge from rest, remember that a charge, whether it's positive or negative, is going to want to decrease its potential energy, right? That's the only way for the kinetic energy to go up. So to decrease its potential energy, in order for delta V to be negative, or delta U to be negative, it depends whether Q is positive or negative for whether the charge wants to go towards the decreasing potential, electric potential, or the increasing electric potential. So what we're saying here is that, so we're going to assume delta U is negative. So in other words, what does the charge want to do? So if Q is positive, then that means delta V is also negative. So in other words, a positive charge wants to decrease potential, and a negative charge wants to increase potential. So if Q is negative, then delta V would be positive in that case. So if you let it go, an electron will want to increase its electric potential. So a negative charge wants to increase V. Okay, so if you let a positive charge go in the middle of this region right here, it wants to decrease its electric potential. So it's going to start moving to the left automatically. It's going to feel a force to the left right there. So it falls this way. This is what a plus charge would do. Now you can grab the plus charge and force its potential energy to go up, but you have to drag it in that direction, right? So this right here, the positive charge moving to the right, its potential is increasing. And because of this formula, its potential energy is increasing. So something external to the electric field has to be doing that. Right? So we'll talk about this a little bit in the next video, but there's a relationship between these equipotential surfaces, what I drew in blue right here, and the direction of the electric field. The electric field points in the direction of the decreasing electric potential. Okay, and this explains a lot why, like, this is another way of looking at, well, a plus charge will want to accelerate to the left right here, and a minus charge will want to accelerate to the right. But in terms of energy, it's because it wants to decrease, each of these charges wants to decrease its potential energy and convert it to kinetic energy. Just as a reminder, you know, if it's doing this, then the total mechanical energy is constant. So this is that statement of conservation of energy, but this time written in terms of electric potential rather than potential energy, right? Just plugging in QV for you. Okay. Yeah, so we'll do an example like this in class. So let's go over that. So again, we're going to look at a parallel plate capacitor because that has the easiest, the most straightforward electric field we can think of, the uniform electric field. In last video, we talked about, this was the formula for the potential energy of a charge Q in the uniform field. So we defined S equals 0 to be where the negative plate was, and then the positive plate is at some distance, S equals D, greater than 0. And it looks like what they did right here was they set plus, like normally there was a plus U naught, right? Looks like they set that equal to 0. So U naught equals 0 right there. Right? So they're not worrying about that. They're just saying when S equals 0, potential energy is 0 right there. Now, remember that we're saying that U equals Q times V. And see how the Q will cancel in there, which makes sense, right? The Q is the thing that's moving around this field, even though the potential energy depends on that probing charge, that test charge moving around in there. The points themselves just depend on the source charges, right? The charges on the plates of the capacitor. So the electric potential is given by this simpler formula. And this is why we prefer potential rather than potential energy, right? It doesn't depend on the actual test charge moving. So the potential is 0 right here, V naught equals 0. And then for any point right here, V equals S times E. And the potential right here would be V equals E times D. Right, so higher electric potential at the positive plate as compared to the negative plate. So higher electric potential at the positive plate versus the negative plate. That's what we're seeing in this graph. This is a graph of, they're superimposing like the plates, just showing where those values are. And that's a plot of V versus position. So it's increasing at a constant rate as you go from the negative plate to the positive plate. And no matter where, so here, because they set U naught equals 0 and V equals 0 right here, they set this equals 0. So you could set V at the negative plate equals 0, but it doesn't have to be. It could just be this value. All that's physical really is the delta V, the voltage between those two plates, or the potential difference between those two plates. So this is actually, in terms of how we deal with creating these potential differences, like we have this picture of the battery. How we would actually put charges on a parallel plate capacitor like this is by taking one of these plates and hooking up to one side of the battery, you know, the plus, sorry, that's the minus side. So just take a wire and touch one side of the battery, and then the positive side you're going to touch to this side of the capacitor. And this is how you would actually create a potential difference. And if this is a 1.5 volt battery, then it's good, then delta V would be 1.5 volts. Right? And then you could infer what the electric field is by using this formula right here. So a lot of times actually the delta V we know first, and then we can use that to create an electric field. Right? The way we've been building this up in class is that we start with the electric field, and then we can define delta V in terms of it. But practically speaking, the delta V is what we have access to. That's easiest. Visualizing electric potential. So this is kind of what I was drawing before. So again, 0 volts and 1.5 volts. The electric field is pointing from the plus plate to the minus plate. That's the electric field vectors, and it's a uniform field, so they're equally spaced. And what we have here, the dotted contours, are two-dimensional surfaces that are perpendicular to the electric field. So the electric field's a vector, it's pointing in one direction. So sorry, probably this way, to the left here. And so that's one dimension, but we live in 3 dimensions. So there's 2 dimensions perpendicular to it. There's a surface perpendicular to that electric field. And all of the points on that dotted surface, and we're seeing a cross section here, all the points on that equipotential surface are at constant potential, equipotential. That means constant potential. So there's one that's halfway in between these two. That's going to be at an electric potential that's halfway between 0 and 1.5 volts. So this one would be at 0.75 volts. And you can interpolate what all the other ones are, right? So it looks like what the book has in this figure is it took the 1.5 volts and it split it out over 1, 2, 3, 4, 5. So it drew some equipotentials inside here. So you start off at 0 volts, and then 1, 2, 2, 3, 4, 5. So it looks like the spacing between the equipotentials that they chose to draw is 0.3 volts for each one of those equipotentials. And they're spaced out so that they increase from the negative plate to the positive plate. And again, this is the source charge creating an electric potential everywhere in space, and it's related to the electric field. We're going to talk more about the relationship between V and E in next video. But right now, it's just getting used to these things, equipotential lines. And this will be really important. The electric field lines are perpendicular to the equipotential surfaces, and the electric field is pointing in the direction of decreasing electric potential. Electric field points in the direction of decreasing electric potential. See how it's pointing to the left right here? That's the direction of decreasing electric potential from 1.5 volts to 0 volts. Right. So a positive charge will be accelerated, and released from rest will accelerate in the direction of the electric field. It wants to move in the direction of decreasing electric potential because it wants to decrease its potential energy. If you let a negative charge go, if you let an electron go, it will accelerate to the right. It wants to increase its electric potential because it wants to decrease its electric potential energy. And so when the test charge is negative, you got to be a little more careful about the sign. So a lot of times it's nice to think about a positive test charge. All right, finally, so that was a uniform field. But remember, we also had point charges. All right, so we're imagining this is our source charge and this is our test charge. So we have potential energy is our test charge times the potential. And we also saw last video that this was K, Q, Q prime over the distance between them. So the potential from a point charge is just K, Q over R. So in other words, we can get rid of the test charge, just pretend this doesn't exist. The source charge creates electric potential at every point around it. And this is how you calculate what the electric potential is from that source charge. It's KQ over R. So it looks like the electric potential goes down. You know, maybe right here it's 10 volts, twice as far away, it'll be half as big, right? The 1 over R dependence. So from this source charge, if that's 10 volts, looks like this would be 5 volts. If you go another factor of 2, it'll be 2.5 volts, et cetera. And this is decreasing all the way down to 0 volts. So this formula assumes that V equals 0 at infinity. So remember, there was some freedom in how you in where you choose the 0 of your potential energy function. There's the same thing that exists with choosing the 0 of the potential. So this formula is simplest. This formula for the electric potential created by a source charge is simplest when you take this, when you have this choice, V equals 0 at infinity. Visualizing the point charge is a little more complicated than it looks a little more complicated than the field inside of a capacitor, just because there's 1 over R dependence rather than a linear dependence. And then if you have more than one source charge, you just add up all of them. So sum of all the KQ over R's. And remember, we can write the K in terms of epsilon. So sum of KQ over R for all the source charges I. So now we're not summing over pairs of charges. We're not looking at interactions between charged particles. We're just saying every source charge has some contribution to the electric potential. We add up all those contributions. So going to this example problem, looks like we're given some information about a capacitor. We're not given the electric field, but we're given a lot of information. We're given the charge density and the distance between the two plates, so we could figure out the electric field. And we're also told that the positive plate is at negative 300 volts. Okay, so we want to find out the potential here. If we knew the potential here, then it would just be the halfway in between those two. So we can solve it a couple different ways. All right, let's figure out the electric field strength. So the electric field inside a capacitor is eta over epsilon naught. So remember, it's from a plane of charge is eta over 2 epsilon naught. And the positively charged plate and the negatively charged plate each contribute the same amount, eta over 2 epsilon naught. So they add together to give this. So the electric field inside a capacitor, in terms of the surface charge density on one of the plates, on the positive plate, like this is the magnitude of it. And so plugging this in, this is 8.85 times 10 to the nanocoulomb per square meter. Looks like this is 10 to the minus 9 in SI units. And this permittivity of free space is this constant. And as long as we had SI units for both, we get SI units of electric field, which is newtons per coulomb. And the 8.85, so we chose this number so that this would nicely cancel, and we don't absolutely need a calculator. So it looks like this is 10 to the 3 newtons per coulomb. And 10 to the 3 newtons per coulomb, there's another way of writing SI units. So instead of force per charge, so let me remind, so remember F equals Q times E. So we could do newtons per coulomb. So electric field was F over Q, newtons per coulomb. But we can also do volts per meter. So another way of writing this is 10 to the 3 volts per meter. And where this comes from is, remember that we had the potential in the capacitor was E times S. Remember, that was one of the formulas for the potential inside the capacitor as a function of S, where S was the distance from the negative plane. So looking at this formula, it looks like another way of writing the SI units for electric field is the SI units of electric potential divided by distance, the SI units for distance, or volts per meter. And so the electric field inside the capacitor is 10 to the 3 volts per meter. And this is great because we can multiply by the distance. We can multiply by the distance separating the two plates to get the total potential difference across the plates of the capacitor. So the delta V, the magnitude of the potential difference between these two plates, is E times the distance. So this is 10 to the 3 volts per meter divided by, and the distance between the two plates is 0.1 meters. So it looks like this is 10 to the 2 volts, or 100 volts is delta V. So is that negative charged is this plane right here, is this at negative 400 volts or negative 200 volts? Maybe pause the video and see if you can guess that one. See, the electric field is pointing from the plus to the minus. And remember, the electric field points in the direction of decreasing electric potential. So the electric potential at the negative plate is 100 volts less. So it looks like the potential here is going to be minus 400 volts. And the potential at point P is halfway between the negative 300 volts and the negative 400 volts. So it looks like this is going to be negative 350 volts. The electric potential at point P is negative 350 volts. All right.